Welcome back, everybody. Excited to dive into a paper today that really gets down into the weeds.
Yeah, we're going to try to unpack some pretty complex physics here.
If you're the kind of listener who loves formulas and algorithms and really getting into the academic detail,
This is the deep dive for you.
buckle up. So we're looking at a paper by Henry F. Legg.
A comment on InAs-Al hybrid devices passing the topological gap protocol. Quite a mouthful.
And it's a comment on a paper that was published by Microsoft Quantum.
Back in 2023 in Physical Review B.
Now, this is all about the hunt for Majorana bound states.
MBSs.
Which, if you've been following along with quantum computing at all,
You've probably heard of these.
these are quasi-particles with the potential to revolutionize quantum computing.
And Microsoft Quantum claimed a high probability of finding these elusive particles.
Using their topological gap protocol,
TGP.
which they claim to be rigorous and unbiased.
And Legg is basically saying, hold on a second.
Yeah, so that's what we're going to unpack in this deep dive. Legg's critique of this paper and really what it means.
For the search for these MBSs.
All right, so to kind of set the stage,
Yeah.
the hunt for these Majorana bound states is a really big deal in physics right now.
It's a hot topic.
And Microsoft Quantum basically dropped this bombshell saying, hey, we think we found evidence for these.
Yeah.
And if they're right, it could be absolutely huge for building more robust and reliable
Quantum computers.
quantum computers, exactly. So what is it about these MBSs that makes them so special? What's all the fuss about?
Well, they have this unique property. They're their own antiparticle,
Okay.
which is kind of a mind-bending
Yeah.
concept. But essentially, it means they're incredibly stable. And that stability is what makes them potentially ideal for building those robust quantum bits.
Qubits.
Qubits, yes. The building blocks of quantum computers.
So Legg is skeptical. Where does he start poking holes in Microsoft Quantum's argument?
He goes straight for the heart of their method, the topological gap protocol, or TGP. Microsoft claimed that this method could reliably distinguish between trivial states and topological states.
And just to be clear, they're looking at these nanowire devices, right? That's where these MBSs are predicted to exist.
Exactly.
So the TGP is like their test, and if it comes back positive, they're saying we found MBSs.
Yeah, that's the idea.
But Legg's saying, hold on, the test itself is flawed.
Right.
So what's wrong with the TGP?
Well, he argues that it all comes down to how they define a gap in the data. This gap is a key indicator of a potential topological state.
Okay.
And it's measured using something called non-local conductance.
So let's back up for a second.
Sure.
Non-local conductance. For those of us who aren't physicists, can you explain that in simple terms?
Okay, imagine you have this tiny nanowire. Non-local conductance is a way to measure how electric current flows through it, but not in the usual way. It's about the current flowing between 2 points that are spatially separated.
Okay, so it's not just like measuring the current from one end of the wire to the other. It's something a bit more complicated than that.
Yeah, that's why it's called non-local.
So how does this non-local conductance relate to the gap they're looking for?
The TGP uses something called a threshold conductance,
Okay.
or G subbed, to decide whether this non-local conductance is effectively zero.
Okay.
And if it is, that signals a gap, which is what they're looking for.
So if the conductance is low enough, that means there's a gap, and that's supposedly a sign of a topological state.
You got it.
Okay, I think I'm following so far. So what's Legg's issue with this? What's wrong with how they're defining the gap?
Well, the paper states that this GUF, this threshold conductance, is set by the maximum non-local conductance at high bias voltages. But Legg discovered that their code actually calculates GUF using the maximum at any bias voltage.
Hold on, so they're saying one thing in the paper, but doing something different in their code.
Exactly.
That seems like a pretty big discrepancy. Why does that matter so much? Why is that such a big deal?
Well, it makes the TGP incredibly sensitive to the specific range of data they choose to analyze. So, for example, Legg showed that simply by narrowing the magnetic field range for one of their devices, it suddenly failed the TGP, even though the region they claimed was topological remained within that new range.
So it's like they're moving the goalposts to get the result they want.
It certainly raises questions about the robustness of their method, because a truly reliable test shouldn't be so easily swayed by these arbitrary choices, right?
Yeah, that makes sense. I mean, if it's so sensitive to how you define these ranges, it's hard to know how much faith to put in the results.
Exactly.
So we've got this inconsistency in how they define the gap, and we've got this issue with the data ranges
Right.
and how sensitive their method is to those choices.
Mm-hmm.
What else did Legg find? It feels like there's got to be more to this story. Like, what else did Legg find that was problematic?
There is. It's not just about the gap definition and data ranges. It's also the data resolution, the pixel size, so to speak. That also had an impact.
Pixel size. Okay, now I'm really lost. How could something like that influence the results of a physics experiment. I mean, we're talking about fundamental particles here, not digital photographs.
Remember that the TGP relies on analyzing patterns in the data, right? And those patterns, they're represented visually as pixels, so changing that resolution, changing the pixel size, can actually change how those patterns are interpreted.
Okay, I'm starting to see how this could get tricky. So give me an example. Like, how does changing the pixel size actually affect the outcome of the TGP?
So the TGP has this thing called a minimal cluster size. And for a region to be considered significant, it needs at least 7 pixels. But if you change the pixel size, well, what constitutes those 7 pixels can change pretty dramatically.
Oh, I see. So like a small cluster that wouldn't have been considered significant before could suddenly become big enough to pass the TGP just by changing the resolution.
Exactly. And guess what? Legg discovered that Microsoft Quantum used drastically different resolutions for different data sets,
Hmm.
even for the same device, and they never explained why.
Without any justification. So it's like they're changing the units of measurement in the middle of the experiment. Like trying to measure a room with a ruler one day and then a yardstick the next. You're going to get totally different numbers.
Exactly. It makes it really hard to compare the results.
Okay, so we've got the gap definition, we've got data ranges, we've got resolution. Anything else?
Oh, there's more. Legg also found that Microsoft Quantum used different cutter voltage pairs.
Cutter voltage pairs.
Yeah.
Now, you've mentioned these before. Remind me what those are. And why does it matter that they use different ones?
Imagine you're trying to measure the thickness of a piece of paper, but you keep changing the angle of your calipers. You're going to get slightly different readings each time, right?
Yeah.
Well, cutter voltage pairs are kind of like the angle of the calipers in this analogy. They're related to how they measure conductance. And Legg showed that changing these pairs can significantly affect whether a region is flagged as topological or not.
Okay, so it's another layer of arbitrariness. Another way they could potentially be influencing the results.
It's certainly a valid concern.
So to recap, we've got a shaky definition of the gap. We've got results that are super sensitive to data ranges and resolution. And we've got inconsistencies in how they use these cutter voltage pairs. It's starting to feel less like rigorous and unbiased and more like pick and choose your own adventure to get the result you want.
And it gets even more interesting when we look at how they applied the TGP to their simulations.
The simulations. Okay, tell me more.
Well, Microsoft Quantum, they claimed they rigorously tested the TGP with simulations
Okay.
and found no false positives, which sounds great, right?
That's what you want. You want your test to be accurate. So what's the problem?
The problem is they never released the code they used for those simulations. They only provided the data.
That's odd. If you're claiming to have this super reliable method, wouldn't you want other scientists to be able to verify it? Transparency is kind of a big deal in science, right?
Absolutely. And this lack of transparency makes it difficult to fully replicate their methods and verify their claims.
Yeah, I could see how that would be a problem. So what could Legg do if he didn't have the code? Could he still test their claims?
Well, even with just the simulation data, Legg was able to demonstrate that the experimental version of the TGP code, the one they actually used for their real experiments, does in fact produce false positives when applied to that simulation data.
So their claim of no false positives, that only holds up if you use a specific version of the code. And it's not even the version they use for their actual experiments.
Right, so it seems their own data contradicts their claims.
Wow, okay, this is pretty complicated. So they're using two different versions of the code, one for simulations and one for experiments. Help me understand this. Why does this matter so much?
The key difference is in how they handle averaging over those cutoff voltage pairs we talked about earlier.
Okay.
The experimental code averages the data over different pairs, while the simulation code doesn't, and this seemingly small difference can lead to vastly different outcomes.
So the no false positives claim only applies if you don't average the data, which is not what they did in their actual experiments. That seems like a pretty big omission.
Indeed, it certainly raises questions about the rigor of their testing.
Okay, so we're already dealing with inconsistencies in how they define the gap, problems with data ranges and resolution, and now we've got these different versions of the code for simulations and experiments. What else could there possibly be?
Well, it gets even more complex when we look at how they define what counts as topological in the first place.
Okay, so remind me, they're not actually directly observing these MBSs, right? They're looking for these indirect signatures in the data.
Right.
But how do they define what counts as a topological signature?
They use this thing called the determinant of the reflection matrix, or DET. It's a way to analyze the data and look for hints of MBSs. And in the original TGP paper, they used a pretty strict criterion. DET had to be less than negative zero point .9 for a data point to be considered topological.
Okay, so there's a specific threshold they're using. What did Microsoft Quantum do differently?
Well, they loosened that criterion significantly. Now they only require DET to be less than 0 at either end of the nanowire for any cutter voltage pair.
So instead of needing like a 90% to pass the test, they're basically saying a 1% will do. That doesn't sound very rigorous at all.
That's a good analogy. And this change, it resulted in a massive increase in the amount of data that could be classified as topological. Legg found that almost 40% of their simulation data met this new relaxed criterion.
Wow, that's a huge jump. It seems like they're casting a much wider net and calling way more things topological than they originally would have. Are you suggesting that they might be intentionally manipulating the data to make it look like they've found more evidence for MBSs than they really have? I mean, that's a serious accusation.
It's important to remember that we're focusing on Legg's analysis here, the questions he raises.
Right, of course.
Whether there was any intentional manipulation, that's a separate matter.
Okay, I understand. It's important to be careful with those kinds of accusations, but it's hard not to be skeptical when you see this pattern of, moving the goalposts and changing the criteria.
Sure.
Is there anything else that Legg found? Anything else that raises red flags?
Yes, actually, the way they determine whether an entire region of data is topological also seems inconsistent. In the original TGP, a region had to be consistently topological to be counted as such. But Microsoft Quantum's paper, they only require a single pixel in a region to be topological for the entire region to be classified that way.
So finding one tiny hint of something topological in a sea of data is enough for them to label the whole thing topological? That seems like a huge leap in logic. How can you justify that?
Well, it definitely weakens the criteria significantly, and it raises the possibility that they could be misinterpreting regions that are mostly trivial as evidence for MBSs.
So it's getting more and more concerning. They're loosening the definition of topological, they're changing the rules of the game, and now they're extrapolating from tiny bits of data. It's like they're building a house of cards here. Is there anything else? Anything else that stands out as particularly problematic in Legg's analysis?
There is actually one final detail that's particularly revealing. Remember that simulation where they claimed to find no false positives? Well, in the figure they published showing that simulation, they conveniently omitted playing the topological pixels.
Why would they do that? Are you saying they were hiding data that didn't fit their narrative?
Again, it's important to focus on the facts and avoid speculation.
Okay.
But Legg points out that if you add those missing pixels back in, almost the entire simulation becomes topological under their relaxed definition.
This is unbelievable. It's like they're performing a magic trick, trying to distract us from what's really going on. So after all of this, where does this leave us? What does it mean for the search for MBSs and the future of topological quantum computing? I mean, if the TGP is so flawed, does this mean the whole search for Majorana particles is a dead end? I'm starting to feel a little worried here. I don't know, this whole thing is making me question everything I thought I knew about the field.
Well, it's important to remember that Legg's critique doesn't completely invalidate the search for MBSs. I mean, it's entirely possible that these particles exist.
So there's still hope.
Oh, yeah.
Okay.
And even that Microsoft Quantum's devices exhibit some degree of topological behavior.
Okay.
But what Legg's paper does highlight is that the TGP, as it stands right now, is not a reliable method for definitively proving their existence.
Yeah, I mean, the potential applications of these MBSs are just mind-blowing. So it would be a huge bummer if this whole thing turned out to be a dead end.
It would be. And the inconsistencies and flaws that Legg uncovered, they definitely cast serious doubt on Microsoft Quantum's claims. And, that has implications for the entire field.
That's a good point, right? Because other researchers have started building on Microsoft Quantum's work, using the TGP as a foundation for their own studies.
Right, if the foundation is shaky.
Yeah, the whole structure could come crumbling down.
Exactly.
So what happens now? If we can't rely on the TGP, how do we move forward in this search for MBSs?
Well, this is where the scientific work begins. We need to develop new methods, explore alternative physical properties
Okay.
that can serve as more robust indicators of topological states. Maybe we need to go back to the drawing board, rethink our theoretical framework altogether.
So this is a setback, but it's also an opportunity to kind of reassess and come up with even better approaches.
Exactly. And sometimes, these kinds of setbacks, they lead to the most exciting breakthroughs, forces us to question our assumptions, explore new avenues.
That's a great way to look at it. This whole deep dive has been a real roller coaster. I mean, we started with all this excitement about topological quantum computing. Then we dove into the complexities of non-local conductance and the TGP, only to find all these inconsistencies and potential flaws. But ultimately, I think it's a reminder that science is an ongoing process, full of twists and turns. And that's kind of what makes it so captivating, right?
It's a journey of discovery, and sometimes the most valuable lessons come from the challenges we encounter along the way.
So what would you say is the biggest takeaway for our listeners? What should they be? Oh, our listeners got something to share. Let's hear it.
Yeah, before the main takeaway, can we back to the fundamental concept? So what's the topological, superconductive, and majority state.
Great question. Let's zoom out for a second.
Yeah, stepping back to basics is always a good idea.
So in the simplest terms, topological superconductivity
Is a state of matter where superconductivity,
which is the flow of electricity with no resistance,
gets combined with topological properties,
which are properties that are protected by the shape.
or topology of the material.
It's kind of hard to visualize.
Yeah, it's like a coffee cup that has a hole in the handle.
Right. You can change the shape a little bit.
But you can't get rid of the hole without fundamentally changing it.
And these topological
Oh, yeah, uh-huh.
Majorana.
Oh, you mean Majorana bound states?
Yeah, let's get into those.
Okay, they're these quasi-particles,
That emerge in topological superconductors,
and they're their own antiparticle.
which gives them really unique properties.
Like they're incredibly stable.
And that makes them promising for qubits,
Does that help clarify the basics?
which, as we've just covered,
is now under scrutiny.
so that's the big picture.
Okay, where were we?
You know, with the benefit of hindsight, I think.
We were about to talk takeaways.
So what's the biggest takeaway for our listeners?
Well, I think the biggest takeaway is that
Science is self-correcting.
exactly, even when major claims are made,
And that even seemingly rigorous protocols
like the topological gap protocol,
can have flaws that need to be addressed.
this process of questioning, testing, and refining is crucial.
Right, and it's important for our listeners to know.
That skepticism is a vital part of the scientific process.
Don't just accept things at face value.
Absolutely. Question the data, question the methods.
Think critically about the claims that are being made.
Like Legg did.
And in the end, that's really what moves science forward.
And to our listeners, we encourage you to continue exploring this fascinating field.
Dig deeper into Legg's paper
Read Microsoft Quantum's response.
and form your own opinions.
The search for Majorana-bound states is far from over.
And who knows what incredible discoveries await us.
Until next time, keep questioning
Keep learning.
and keep diving deep.
Thanks for joining us.
And remember, the quest for knowledge is never over.